Okay, so for discussion 7, I had B04 for my data set. So that means I was doing the birth weights of Minnesota and Iowa in 1996. So we are going to be focusing mainly on this set of data right here. So the first thing that I did was, because we'll get back to this later, was I calculated my own set of descriptive statistics and I made my own box plot. So down here, bear with me for a second, here it is. So I just created my own descriptive statistics boxes. So I determined the mean, the min, the max, the standard deviation, the quartile 1, 3, and the median of each of these sets of data. And from there, I created a box plot using the hidden box, middle box, and upper box. And I did all of this by looking at a YouTube video. So if you need help making box plots, there's some nice YouTube videos out there. And so what I did is I just made this box plot so we could really look at the difference between Minnesota and Iowa. And as you can see, this is Minnesota and this is Iowa. They look pretty similar. Just in terms of where their median and their average actually is. The Minnesota box seems slightly higher up due to its median of 7.63 and its mean of 7.5 as opposed to the 7.43 and median of 7.5. But other than that, it is seemingly even. So that could give us some predictions as to what we could think about the null hypothesis and the alternative hypothesis in the next step coming up. So, but now we're going to do the 5-step hypothesis test. So, coming over here to this next sheet, the first step is to make our hypotheses. So my null hypothesis is Iowa and Minnesota have equal means, which the mean would be 7.43 because we're going to assume based off of Iowa. And then our alternative hypothesis would be Iowa has a higher mean than Minnesota of 7.43, which would be greater than the mean of our second distribution. Ignore this right now. So the first things that we have to go through are our assumptions. So we can assume it's a random sample because Professor Barron told us it was a random sample, and we can assure that. The 10% condition, 500 people from each state is definitely less than 10% of the entire population we are looking at, since that is probably hundreds of thousands of people. And then the success-fail condition, we definitely can assume that more than 10 people are less than the mean, and more than 10 people are greater than the mean. So those are all check, check, check. We can clear those up right away. The next thing that we have to do is calculate our test statistic, which we already had the lovely data for, so we didn't have to do that calculation, but we took the signal and the noise to get this test statistic of negative 0.86. From there, taking this negative value, we plugged it into our p-value equation, which was also nicely provided for us, and I just plugged in the test statistic value of negative 0.86, and that would turn us out to our p-value of 0.19. Right over here. So, I think I forgot a step. Let me just back up for a second. Before we even calculate the p-value, we'll just ignore that for a second. This is our graph. So this is what we would be assuming if we did not calculate this p-value yet. So if we just took this test statistic and we graphed the test statistic on a number line. So I graphed it about maybe if I moved it over a little bit there, 0.89. And then this is just the lovely drawing of a bad curve that I could do in Excel. But our high point of the graph would be at our mean, so that's about 7.43 right there. And we can assume to see the ramp up and the ramp down. So putting our test statistic here, if I had to make some type of prediction of the percent that was underneath that, I would say, personally, I would probably say between 5 to 10% of the entire area of the graph. So then from there, calculating our p-value, we take our test statistic, we plug it into our p-value equation, and then from there we got about 0.19, which is about 20% if we multiply that by 100 and we round to 0.2. So that is a highly positive p-value that we have there. So if our significance threshold is 0.01, 0.19 is way above that significance threshold. And since it is far above our significance threshold, we can say based off of this, our p-value is so much larger than our significant threshold that we can retain the null hypothesis, is what I would say. And I'd say this because the results are consistent with Iowa and Minnesota having equal or highly similar average weights for babies born in 1996. I would go as far as to say that. Finally, to finish it up, we calculate our confidence interval. So I calculated 99% confidence interval. I used a t-value of about 2.6. So I took our means, I made the difference, I did plus or minus our t-value, multiplied the square root of the standard deviation of Iowa divided by the number, and then same thing for Minnesota, the standard deviation divided by the number of participants, and I came out with 0.123 blah blah blah. It goes on and on and on. So putting it in perspective on our nice number line graph, it would be a positive. Oh, is that negative? Oh my goodness, that is so incorrect. Silly me. There we go. That's where it should be. So that is about where our confidence interval would lie on our number line. So we can say with 99% confidence that our mean is going to be within 0.123 continuous numbers within the means. So the means will most commonly be within that range of the average. So finally, the averages of Minnesota and Iowa slightly differed by 0.07 pounds. So 0.07 pounds can seem like a high number, but in reality it's less than an ounce, and in birth weight that isn't a very significant amount of weight. So I would say these results are highly similar and seemingly acceptable. If they were not seemingly acceptable, that would mean we got a false positive for our hypothesis, which would make it a type 2 error, but I do not believe that there is an error. I think that their averages are similar, so similar that they can be seen as seemingly acceptable. So, thanks for watching!